Hi, you guys. Welcome to Membranes 5. We continue along, and now we start with the concept of tonicity of a solution. Tonicity is a term that gets confused a lot, because when we talk about tonicity of a solution, we're not talking about how many milligrams of a solute there are in that solution. We're not talking about number of molecules. We're only talking about what that concentration is relative to the concentration of solutes in a cell. So it's just a comparison. It doesn't come with units. So we always talk about the tonicity of a solution, never of a cell. We don't say that a cell is hypertonic. No, cells are happy, living at 0.9% salt solution. It's the solution that can be incorrect. So I'm telling you here, tonicity of a solution describes the volume change of a cell at equilibrium. The volume change of a cell. In other words, if you get a cell and put it in ocean water, what's going to happen to the volume of that cell? If you get a human cell and put it in tap water, what's going to happen to the volume of that cell? That is tonicity. So they could be hyperconcentrated, that solution. It could be hypertonic, very concentrated, a solution with a higher solute concentration than that of a cell. So that is the example of the ocean. It's hypertonic. You put your cell in the ocean, what happens? Water is going to move out of that cell towards the higher solute concentration. So the ocean is a hypertonic solution. The opposite of that would be hypotonic. A hypotonic solution has lower solute than that of a cell, and water moves into the cell. This is tap water. Tap water, you put your cell in, and what would happen is that water moves into it, and it could move in and in and in and in and burst. Not a good thing. So what is the perfect solution for a cell? That's isotonic. An isotonic solution, there is no net movement of water. This is a solution that is like saline solution, 0.9% solute. That means that the cell lives happily ever after in this kind of concentration. Okay? Remember, it's always relative to solutions. These diagrams are very, very helpful, and they're in your book. So let's look at what would happen if you had a hypotonic solution. So on the left of your screen, you have a cell. It's immersed in a beaker that has some fluid in it, and we have these little ends, which means non-penetrating substance, which means it does not cross the membrane. This end cannot come out. This end cannot come in. So the only thing that could possibly move is the water. So if this was point A, you would start here. What would happen over time? Well, ends can't move, right? The little balls cannot move. So instead, water is going to move in to where there is a higher solute concentration. And now this ball here seemingly looks larger because water has moved in. And we would know then that that solution was hypotonic. If you had no other way of knowing and you knew that there was swelling of the cell, you knew that it was hypotonic. Great. Now, let's add a complication. We have our cell here with the little ends, which are non-penetrating solutes, but let's put that in a solution that has both solutes that are non-penetrating, the green balls, and solutes that are penetrating, the purple balls, and put this cell in the solution. What's going to happen? Well, there are 6 solutes here. 1, 2, 3, 4, 5, 6. And over here, there's 6 solutes. 1, 2, 3, 4, 5, 6, even though some are green and some are purple. So the solute concentration inside the cell and the solute concentration outside the cell is the same. So they're isoosmotic, which means there's no difference in the concentration of solutes either in or out. So what's going to happen? Well, at first, you put the cell in, and it seemingly is in equilibrium given the 6 solutes out and the 6 solutes in. So let's call that initially. So I'm going to read it to you. When the cell is placed in the solution, no water moves initially because the cell and solution are in osmotic equilibrium. But now what's really going to happen is that these P's are penetrating. It means they're either small enough or they're lipid soluble, and they will have the ability to go from where they're more concentrated to where they're less concentrated. In other words, down their concentration gradient. Will they do it? Yes, because molecules tend to move down their concentration gradient. So it will move from out here inside. And then what's going to happen? I no longer have 6 in, 6 out. So let's move there. Concentration gradient has happened. There used to be a P here, but it's now moved in. Now I have a problem because there's fewer solutes out, more solutes in. If there are more solutes in, what will water do? It'll follow and go towards the higher solute concentration. Remember, solutes suck. So that's going to happen. And then what's going to happen? Well, if more water moves in, maybe another P moves in, and more water moves in, I could potentially burst the cell. I'll read this to you. Equilibrium is restored when the concentrations of non-penetrating solutes are equal in the cell and the solution. The cell gained volume at equilibrium, therefore the solution was hypotonic. In this case, it didn't burst, but we could have a situation where enough of those penetrating molecules could move in and burst the cell. So this is to illustrate that the total number of solutes may be equal, but if some have the ability to cross the membrane, that equal number is no longer going to be valid. It's no longer going to stop water from moving. I'm going to stop this one here and go on to one more short video. Thank you. Thanks for listening.